Okay, hi guys. I hope now it's working. I just made the entire stream and it did not work. I hope this time you can see me. Let me check. Does it work? Yes, it does. Oh, yes, now it does work. All right, perfect. So I'll just do it again. So I'm back to YouTube, hopefully. Again, no promises. Hopefully I'm back. And today we're going to do Structure 1.3 for IB, both SL and HL, but only multiple choice questions. So these are the questions on electron configurations. And because I've already done this stream, but no one saw it, let's do it fast and efficient. Okay. First question, yes, and at first I'll solve SL questions, then at the end there would be HL questions. So if you are an SL student, you can just stay if for the SL questions. If you are an HL student, you have to do both. Yeah. Then all the questions are from Save My Exams. I'll link them below. First question. There are six unpaired electrons in atoms of element Z. What could element Z be? Okay, let me just open my notes. Yes. Okay, so what could element Z be? So it has to have six unpaired electrons. Let's see. So what we do, we need to check the electron configuration, right? So for, okay, uh, checking for a sulfur. Sulfur, there it is, 16 electrons. Let's write an electron configuration. It's 1s2, 2s2, 2p6, that's 10, 3s2, 3p4. Right, and the only way, the only place where you can have unpaired electrons, it's when the orbital is not full, right? So here you have all subshells that are full, which means that the only place where you can have six unpaired electrons is in 3p, which is not possible, right? Because it only has four electrons. So it's not A. Just in case, let me remind you. So p orbital, it has, well, let's write maybe 3s and 3p just for illustration. So 3s is 1 square, so it has one orbital. 3p and any p subshell, it would have three orbitals. So 1s2, two electrons, that's complete. 3p4, remember we fill it one electron at a time. So 1, 2, 3, and then the fourth one would be paired. So you see it has only two unpaired electrons, but it was clear, right, that it cannot have six because it has four electrons, so not sulfur. Then let's check iron. Iron has how many electrons? 26. Okay, so let's write down the configuration. So 1s2, 2s2, 2p6, 3s2, 3p6, that's 18, 4s2, 3d6. 3d6. Right, so the only place again where it can have six unpaired electrons is in 3d. So let's draw it out. 3d has five squares, five orbitals, right? Because 10 electrons is the maximum. In 3d, each orbital can hold two electrons. So 3d6, 1, 2, 3, 4, 5, 6. How many unpaired electrons do we have? Well, not 6, 4, right? So not B. Carbon. That's a 1 minute question, right? Remember. Carbon, 6 electrons. Well, that's not even an option, right? Because for 6 electrons, like you can't have them all unpaired. So not C, I'm not even checking. I wouldn't check A as well. Yeah. So I maybe would have checked iron, but to save time, yes, A, I wouldn't check in the exam. C, I wouldn't check in the exam. Chromium, yeah, so it must be chromium. Let's see. I will write it out just to remind you that it's an exception. Yeah, so chromium has how many electrons? 24. Why doesn't it go away? 24 electrons. And if we were to write chromium electron configuration normally without remembering that it is an exception, you would have 1s2, 2s2, 2p6, 3s2, 3p6. Remember 4s, yeah, 4s2, 3d4 would have been 3d4. Because that gives us 24 electrons. But we are smart. We remember that chromium is an exception. And that exception is where it is here. So instead of having 4s2 3d4, it would have 4s1 3d5. So why that happens, that's not our problem. It just happens like this. They say that exactly half-filled 3D is more stable. That's why an electron is promoted from 4s to 3D. And these are your 6 unpaired electrons, right? So 4s1, all of these are paired, obviously, right? Because the subshells are complete. So 4s1, 3d5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, one at a time, so 6 unpaired electrons. Good. Next question. The diagram shows 3 orbitals labeled 1, 2, and 3. What is the correct label for each orbital? The spherical one can only be S. So it's not A, yeah, because it starts with a P. The dumbbell shaped, it could be, well, it's only P, but there are 3 types of P orbitals: Px, Py, and Pz, depending on how they align, right? So Px aligns along the x-axis, Py along y-axis, and Pz, guess what, aligns along the z-axis, yeah. So this is Px, this is x, this is S, this is Px, and this would be then Py. So it is D, Px, Py. In this case, it doesn't really matter how you, obviously they already drew them out, but for an open response question, so if you have a question that just asks you to write down, to draw the shape of the p orbital, you can just write it at a dumbbell shape no matter how you align it. The most important part is that the lobes are the same. Yeah, so if you skew the lobes, it means that you're writing a hybridized orbital here. But again, if they just ask for the shape of the p orbital, just draw the dumbbell shaped. But if they ask you to write the px orbital, let's say px, yeah, then you have to also show the axis and align the p orbital alongside the correct axis, yeah, so the x-axis. That's for paper 2. Next question. Still a cell, yeah. What is the electronic configuration of an ion with a single negative charge and atomic number 17? Single negative charge, atomic number 17. So what do we do? Let's just see what element that is. That would be chlorine. Yeah, 17 electrons. Chlorine, 17 electrons. I'll write down the electron configuration and then add 1 electron. So 1s2, 2s2, 2p6, 3s2, 3p, 3p, that's 10, 12, 3p5, right? And that's chlorine, and then single negative charge, so add 1 to the outer shell, becomes 3p6, which is 1s2, it's a B, right? B. Next. What is the correct sequence for the orbitals shown in an atom of vanadium in order of decreasing energy? Decreasing energy. So when we're filling the electrons in, we're filling them in order of from lower energy to higher energy, yeah? So in vanadium, well, in any element, it doesn't even matter whether it's vanadium or not. So it would be 1s2s2p, 3s3p, 4s3d, right? So that's the order of increase, like the energy increases that way. Energy increases, and what do we do? We want in order of decreasing energy, so the other way around. Yes, so from 3d, so 3d would be the height, so it must be d. Yes, so 3d, 4s is lower, 3p is lower, and then 3s is even lower, so it is d. Next question, question 5. An element in the D block of the periodic table forms a 4 plus 4 ion and has the electron configuration of argon 3d1. Okay, I don't like this notation, the condensed notation, argon 3d1. Let me rewrite it normally, yeah, because I think a lot of people don't see what argon is. What argon is, so I'll just rewrite it just in case. So argon is 18 electrons, so it just means that the first 18 electrons are 1s2, 2s2, 2p6, 3s2, 3p6, that's 18. 3d1. So that's my configuration for an ion. Yeah, that's x plus 4. And then how do we get x plus 4? So x plus 4, like it is formed when x loses 4 electrons. And remember which electrons are lost first. Electrons from the 4s, yeah? So 4s electrons would be lost before the 3d. So it means that this X ion, what did it do? Well, it lost 4s2 electrons, right? And the other 2 electrons it must have lost from the 3d. So also 2 electrons must be added there. So the configuration for X would be, well, I will rewrite it. 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2, 3d3, right? And then let's check. So if it's losing 4 electrons, what happens? Well, we're losing these 2, and again 2 from 3d, so becomes 3d1, so all good. Yeah, so that's my configuration for the element X. And now we just have to see which one it is. So it has how many electrons in total? It has 2 plus 2 plus 6, that's 10, 23. Yes, so X has 23 electrons in total, which means that it has atomic number is 23. 23 would be vanadium. C. I got vanadium last time when I was doing this stream, which no one saw. Okay. Next, deduce the correct information about the element tin. Z equals to 50. Z is atomic number. Right, so we just find it in the periodic table. So the number of occupied main energy levels is shown by the number of the period. Yes, so I'll just find tin. Where is it? 50, right? So it is here. It is here, so it is in period 5, which means that it has 5 occupied energy shells. So C or D, and the number of electrons in the highest main energy level equals to the number of the period, to the number of the group for groups 1 and 2. So for example, for these guys, we know that they have the group 1 has 1 electron in the outer shell, group 2 has 2 electrons in the outer shell, but then from 13 to 18, a number of electrons would equal to group number minus 10. So for tin, it's 14 minus 10, right? So 4 electrons in the outer shell, so C. That's fine. Yes. You're allowed to write to message in the chat, right? Because now I'm live. Finally. Next question. Which species produce a half-filled set of p orbitals on losing an electron? Half-filled set of p orbitals upon losing an electron. Think about it. So they form what? They form P3, right? So completely filled P sublevel, it's P6. So half filled exactly is P3. So when they lose an electron, when the species loses an electron, it must become P3. Well, let's see. What I'll do is I'll write down electron configuration for the species and see what happens when it loses an electron. Yeah. So for lithium, well, lithium plus I wouldn't even write because lithium plus is nowhere close to P. Yeah, so it doesn't have a P subshell at all, so not lithium. Fluorine could be. So fluorine, how many electrons does it have? It has 9. Okay, let's write it down. So fluorine has 9 electrons. 1s2, 2s2, 2p5. Yeah, that's fluorine. When it loses 1 electron, what happens? It becomes 2p4, not 2p3. So that's not B. Nitrogen. Nitrogen is 7 electrons. It is 1s2, 2s2, 2p, what is it? 3, right? 2p3. 2p3. If it loses an electron, it becomes 2p2, not p3, so not C, and it must be D, right? If I was in the if you're running out of time, just choose D, do not check, but we can check. So N minus, well, we already know the configuration of N. Yeah, that is 2p3, so it means that for N minus it is 2p4. And then now when this guy loses an electron, it becomes 2p3. That's what we need, right? So it loses one electron, so it becomes p3, so it is D, exactly half filled p orbitals. Next question. Which statement explains why electrons pair up in orbitals before occupying an orbital of a higher energy level? This is a common sense question, okay? It's not like you're studying this, but let's just look through the options. So, what do they ask? Why electrons pair up in orbitals before occupying an orbitals of a higher energy level? So, like, why do they bother pairing up if they could just stay unpaired and go to higher energy levels so that they stay unpaired? Yeah, so why does that not happen? Why do they start pairing? Let's look through the options. The energy from repulsion is greater than the jump to a higher orbital. Just think about it. So the energy from repulsion is greater than the jump to the higher orbital. So electrons are lazy, right? They want to do things that would require the least energy. So if the energy from repulsion was greater, they would jump and they would jump to a higher orbital, which means that we would not see the paired electrons at all. So this statement is like the opposite to what's happening. So that's wrong. B. Electrons occupy higher energy orbitals before lower energy. That's a completely false statement, right? So electrons occupy lower energy before the higher. So not B. Electrons in lower orbitals have higher energies. False statement again. Yes, so in lower orbitals, electrons have lower energies. So must be D, but let's check. The energy from repulsion is less. Yes, it is less than the jump. So that's why they prefer to pair up rather than jumping to the higher orbital. So like it's opposite to A. So that's a D. That's the answer. That's still SL, right? Still SL. A line emission spectrum occurs when? Okay, line emission spectrum. Emission means that energy is, well, electron goes from the higher energy to the lower energy. And these statements, you see, there are two parts. So electrons release energy or absorb energy, and then they move from high to low or from low to high. Well, actually, yes, let me remind you the emission spectrum of hydrogen, like what happens. So if we think about energy levels, yes, so these are energy levels, they get closer as we go up, and this is energy going up. So this is, let's say, level 1, level 2, level 3, 4, and so on, yeah. So in in any element, so in one electron system, so normally in the ground state, electron is here. Remember, they're lazy there in the lowest energy level. Now, if you do something, if you supply voltage, for example, or a very high temperature, an electron would jump somewhere up, and after that, it cannot stay on higher energy levels forever. It would go back. Yeah, so it would go down to lower energy levels. So it can go either completely back here or maybe there. Yeah, so it would relax to lower energy levels. The most important thing is that it can only jump between the levels. So when it falls down, it releases the electron. It releases energy that exactly corresponds to the energy gap. So for example, if it falls from 2 to 1, what does it mean? It means that it would emit a photon of light, which frequency would correspond to that energy gap. Okay? And so that's why we see a line spectrum. So we don't see a continuous spectrum. We don't see all possible energies, because an electron, it cannot jump, for example, from here to there because there is no energy level here. So that frequency we would never see, right? And that's why it's a line spectrum. But I don't know why I'm telling this. It doesn't maybe it won't help us to solve this question, but let's see. So, well, yeah, it will help because we know that okay, so a line emission spectrum occurs when? So the energy, is it absorbed or released? So we see it, the line, when the energy is released, right? When it falls down. So it's not C, it's not D. And then energy is released when electrons move from high to low. So it is A. From higher to lower energy level. Right. That's fine. Yeah. Next question. Still SL. Which statement is true about the spectra shown? Yeah, well, this is the spectra. So this is what we measure when the photons are emitted, right? So we measure the frequencies or wavelengths that are emitted or energies. So if we have a red end on the left and blue end on the right hand side, it means that energy increases to the right. Yes, so energy increases that way because blue light has a higher energy than red light. And it is in the data booklet, but I highly recommend to know it because it would make your life so much easier and you would just solve everything faster. So energy increases that way towards the blue. Then also frequency increases that same way, increases, and the wavelength would decrease, right? So blue light has a lower energy. Sorry, blue light has higher energy, a shorter wavelength. A wavelength decreases, right? So let's read the statements. All lines in R have the same energy. False, because we said energy increases that way, so this line has a lower energy than that one, so not A. Q and S could represent the line emission spectra. Q and S can represent the line emission spectra. Well, that's when we need our small diagram, yeah? So you see that as electron and like energy levels have you move towards higher energies, the energy levels get closer to each other, which means that the energy gap between them would become smaller. So it means that the energy levels, the frequencies, yeah, or the lines, they would converge at higher energy. So if energy increases that way, it means that lines have to converge, so become closer to each other here. So S, yes, S is the emission spectrum. In Q, the opposite happens. So Q would appear if we had larger gaps at higher energies, right? Because the lines get further away. So Q is not an emission spectrum because it never happens in real atoms. So in real atoms, energy levels get closer to each other at higher energy. So it's not B. Only S could represent the line emission spectrum of hydrogen. Yeah, that's correct because that's the only one where we have lines converging at higher energies. So Q is wrong, R has equal distances, P does make sense. So C is correct, and P indicates the element has 4 pairs of electrons. That's completely wrong because this works for one electron systems. Otherwise, we have to take electron-electron interactions into account. Okay, finally HL. HL, SL, guys, you are free to go. Thank you for watching. HL. The second ionization energy of magnesium is 1451. Which equation correctly represents this statement? Okay, second ionization energy definition. Yes, remember first ionization energy, it's when you remove an electron from a gaseous atom. Let's write the first ionization. So for magnesium, the first ionization energy, it's energy for this reaction. So you take magnesium gas and form magnesium plus and an electron. That's first ionization energy. Well, enthalpy change of this reaction is the first ionization energy. Right. Yeah, and by the way, if it was paper 2, if it was open response question, if you don't plug this small g, you lose a mark, right? And that g, it must be readable because when I'm marking exams, if I'm kind of unsure whether it's S or G, I'm allowed to mark you off. So yeah, just make it readable. When I write, when I writing exams myself, sometimes I say, okay, what is it G or S? But yours G must be readable for the exam purposes. Okay, so first ionization, then second ionization. It's when you take whatever ion was formed, so Mg plus, and well, remove another electron, right? So Mg2 plus and an electron. So that's the second ionization. So you see the charge of the ion matches to the number of the ionization energy. So it must be either A or B, yeah, because in C it's the sum of first and second, so they remove 2 electrons at once. D is first ionization. Right, and then we just have to decide whether it's positive or negative. Well, we need to supply energy, so we need to overcome the attraction between the ion and the electron, which is an endothermic process. It's kind of like bond breaking. It's not bond breaking, but it's overcoming the attraction, yeah, and that's always endothermic, so it is B. So energy must be absorbed. Next. Right. X, Y, and Z are consecutive elements in the third period of the periodic table. Element Y has the highest first ionization energy and also the lowest melting point. They are consecutive, so they go like one after another. Y has the highest first ionization and lowest melt. Well, let's look at melting point first. So option A, silicon, phosphorus, remember phosphorus is P4, sulfur is S8. So if we think about melting point, which one would have the highest? Well, silicon, because it's giant covalent. These guys are simple covalent, which means that they would only have London forces between the molecules. So the more electrons they have, the higher the melting point. P4 has the lowest number of electrons out of these two, so it's lowest melting point, so that works. This is fine, that works, and also the highest first ionization energy. That's also correct because as we go across the period, remember in general, the first ionization energy would increase, but there are exceptions, and sulfur is one of those exceptions, right? So sulfur would have a lower ionization energy than phosphorus because remember there were two unpaired electrons, so there is an electron-electron repulsion, which makes the first ionization energy smaller. I'm just thinking, should I go into details? Let me not go into details just yet. Yes. So if you remember this trend, it's fine. If not, I think there would be another question where we can talk about it, or maybe not. I just did this stream and I already forgot. But yes, so in any case, A is right. Melting point for phosphorus is the lowest. Ionization energy is the highest because the sulfur was an exception. Yeah, it's lower than phosphorus due to repulsion of 3p4 electrons. Next question. Which of the following calculations gives the correct calculation to find energy for a photon of blue light with that wavelength? Okay, let's see. What do we need? We need energy in kilojoules. Right, so the formulas. The formula for energy, it's Planck's constant times frequency. It is in the data booklet. And there is another formula that speed of light, it's wavelength times frequency. We have, what do we have? We have wavelength. So if I rearrange it so what I want to do is I want to do it all in one go. So I will just rearrange this to find frequency and plug it in there. Yeah, so let's see. Right, so frequency would equal to then what? C over wavelength, yeah? And then if I plug it in, it would be H times frequency, so C over wavelength. And that's it, plugging in. So H, it's 6.626 times 10 to the minus 34. C, speed of light, 2988 times 10 to the 8th over wavelength. Okay, and here comes the most common exam mistake. This is in nanometers and the units must be meters because the speed of light is in meters per second. So I need to convert it to meters, which is to convert from nanometers to meters, you multiply it by 10 to the negative 9. Nanometers times 10 to the negative 9, and then we calculate. Okay, times 10 to the minus 34 times 2988 times 10 to the power of 8 and over 550 times 10 to the power of negative 9, which is 3.60 times 10 to the minus 19. And the units for this would be joules, right? Because you see, always look at your constants. This is joules times second, so that's joules. And we need what? Of course, we need kilojoules, right? They never ask, I mean, they can ask in joules. Actually, I've seen questions in joules, but double check. Yeah, so that's kilojoules. To convert from joules to kilojoules, we divide by 8,000. So 10 to the minus 22. 3.6. That's a C. Next, okay. Next question. Successive ionization energies for an element Y are shown. Okay, successive ionization energies. What is that? Successive ionization energies, it's when you're removing electrons one by one. Yeah, so you starting from the outer shell. And generally, the successive ionization energies would increase, which means that every next electron it's harder to remove, right? But it wouldn't increase linear, so you would see jumps in ionization energies, and the jump happens when you move the shell. Yeah, so for example, if you think about it this way, I'll quickly draw. So if this is the nucleus, yeah, let's say this is energy level 1, this is energy level 2, and let's say we have like 2 electrons in the first shell and maybe 3 electrons in the second shell. So the successive ionization energies, what is it? So you remove the first electron, energy needed for that, it's the first ionization. Then you remove the second electron from there, then the third, and the first 3 ionization energies would become more and more endothermic, right? So more energy would be needed. But then you would have a jump because the fourth electron would be removed from the first shell, which is much closer to the nucleus. So essentially, you're looking for those jumps to find out how many electrons are there in the outer shell. I hope that makes sense. Now let's see. So I'm looking for a jump to find out how many electrons Y has in the outer shell. So I can see that it's from the second to the third. You see that's a high increase in ionization energy. If you cannot see that jump, then what you should do is you should approximately calculate the difference between the first and the second, second and the third, and so on, without a calculator, okay, guys? Because you have 1 minute for this question, so it has to be approximate. So, for example, between the first and the second, approximately we have 700 kilojoules. Between the second and the third, well, approximately 6,000, yeah, even more. Between these, it's like 3,000. And then again, what is it, like 3,000 approximately, right? And you see 6,000, it's much higher than what was before and much higher than what comes after. So that's your jump. And that means that after you've removed the second electron, you change the shell to closer to the nucleus. So it means that that element Y has 2 electrons in the outer shell, which means that the charge would be 2 plus. So B. Good. Good. Next. Next, values for the successive ionization energies for an unknown element are given below. In which group? Well, same question, yeah? Can you see the jump? Well, there it is. Yeah, that's about 3,000, and this is 1,000. This is 8,500. So, jump after the first ionization energy means that it's group 1. How many questions left? Okay, 2 questions left. I'll try to finish it before my next lesson. Okay, let's see. So the graph shows the first ionization energies of some consecutive elements. Okay, consecutive elements. So it means that we're moving across the periodic table. Yeah, so elements are one after another. Which statement is correct? What can we tell about X right away? What we can tell is that it has the highest ionization energy in its period, right? Because it goes up, reaches the top, and then falls down. This is the pattern when you reach the end of the period and then change the period. So you see, if you go across the period, you get the highest ionization energy, and then, for example, you go from argon to potassium, and then it drops because suddenly you're in group 1. So we know right away that X is in group 18, so it's a noble gas. We didn't even need all these exceptions, right? So generally it increases, reaches the top. Noble gases have the highest ionization energy, first ionization energy, because they have the most protons, then drop down because you're going to the next group, to the first group and next period. Okay, final question. Which transition on the diagram corresponds to the ionization of hydrogen in the ground state? Ionization, what is it? It's when you are removing an electron completely, right? So an electron goes to infinity. So it cannot return. It cannot everything, all the electrons that are returning, we see them in the emission spectra, right? The electron, if you supply high enough energy, you kind of push it to infinity, it can't return back. So, okay, so it must be to infinity, and ground state means that it's jumping from level 1 by definition. Yeah, so when an electron is in the lowest energy level, that's the ground state. So it's not C, not D, because here it's from level 2. Well, and ionization, it's going from the ground state to infinity, so electron is removed. So it is A. In B, electron is added. Yeah, so it's when you're adding an electron. So it's kind of like electron affinity, B. Yeah. Okay, the answer is A for this one. So that's it. I let you go. Um, as if I'm finishing my lesson. So thank you for watching. If you have any requests for the future topics, you can send them to the comments. I'm reading the comments, and because I try to make this in order to go through all the topics in order, which I have such a huge, huge, time gaps between my streams. So I think I can cover any topic. So if you have any requests, you can write it down. Okay.